Welcome to What's New in AR. I'm Jared Finder, Engineering Lead for AR Core, and I'm joined by Eric Lai, Product Manager for AR Core. In this session, we're going to talk about what AR Core is, improvements we've made over the past year, and some new capabilities that we are excited to announce. First, a quick introduction to AR Core. AR Core is Google's platform for building augmented reality experiences on mobile devices for both Android and iOS. We want augmented reality to be available to everyone and work on existing devices. Augmented reality, or AR, is a technology that enables completely virtual objects to be placed in the real world. The virtual objects get drawn on top of the camera image, and when drawn correctly, they blend in, almost like they're actually there. This augmentation of reality allows apps to show information in a more natural, more human way, such as pointing exactly down the street to turn on, allowing someone to remotely help you by adding 3D annotations, or immersing yourself in a virtual art piece. There are many different capabilities that enable AR. We group these all together into the AR Core skill tree. We've been steadily leveling up foundational capabilities while adding new ones since AR Core was first released in 2017, working on ways to make our technology faster and more accurate without requiring people to buy new mobile devices. AR Core is available on over 1.2 billion active Android devices. And so you can build cross-platform AR apps. Select features are available on iOS as well. We support the iPhone 6S and up. AR is used by core Google apps, such as Google Maps for walking navigation, as well as by third parties, such as TeamViewer, for remote AR assistance solutions. Now, a key request we consistently hear from app developers using AR Core is that they want the core capabilities that let objects feel real to be faster and more reliable. In the real world, objects don't glitch in and out of existence when you turn your head. Users expect the same from virtual objects in AR. Motion tracking is core to enabling immersion in AR experiences. By tracking how the phone moves through the world and where the floor, tables, and walls are, an app can place virtual objects on those surfaces and have them stay anchored in place. The virtual objects need to always be drawn appropriately, even as the phone moves around, so that they feel as if they're actually part of the world. Over the past year, we've made significant improvements to motion tracking. We've reduced the average time it takes for motion tracking to start up and a plane to be found by 17%, and we've reduced the amount of time motion tracking gets lost by 15%. This allows experiences to start up faster and be more reliable, all without any code change needed in an AR Core app. But we want to do better. And thanks to Google's investment in machine learning, we can. Late last year, we started an experiment where we use ML to drive motion tracking in cases where the camera image is not enough, forced here by turning the screen black. This experiment resulted in faster initialization and a further reduction in the amount of times motion tracking gets lost. You can see in the video on the right how motion tracking is able to continue appropriately, even when the screen goes black. We are currently rolling out these ML-driven improvements to all users of Live View in Google Maps. Another key part of immersion we've been improving is depth. Depth enables AR experiences to have more interactions with the real world. We use the existing camera on a smartphone to build a depth map, which captures the shape of the world out to 8 meters, or 26 feet, about the size of a big room. Here you can see a video representation of the depth map, where the color changes from red to blue based on how far away that pixel is. One thing this enables is occlusion, where virtual objects appear behind real ones. This is valuable in all AR experiences. Here you can see the same scene with and without occlusion. Without occlusion, the penguin appears in front of the potted plant, making it not look like a part of the world. With occlusion, the penguin is properly drawn behind the potted plant, and immersion is maintained. This also enables interaction, where virtual objects can now properly follow the non-plane shapes of surfaces in the world. This is from TeamViewer. See how the line follows the shape of the printer as if it were being placed there in reality. Here, too, we've leveraged machine learning to improve the speed and coverage of depth. The average time to initial depth is reduced by around 15%. The average overall coverage of the depth map is now at 95% and is dramatically improved on surfaces with minimal texture, as you can see on the empty white wall and on the black TV. These are places that classical depth would struggle with due to a lack of visual features. Depth coverage is now comparable to the amount of coverage in dedicated depth hardware. This also helps out motion tracking, with a further 8% reduction in the time to the first plane and an increase in the number of planes accurately found of about 25%. And on select Pixel phones, we can use the existing second camera to get the depth even faster. This dual camera depth further speeds up the time for initial depth while also speeding up motion tracking too. It only needs to run for a little bit at the startup, so this has a minimal effect on battery life. This is currently rolling out for Pixel 4 and Pixel 6. And I'm excited to announce that we have just released long-range depth, which is available now. With long-range depth, depth can be detected up to a range of 20 meters or 65 feet. Here you can see long-range depth map near one of the Android statues on the Google campus. With this increased range, depth can now be used in outdoor situations in addition to the indoor ones. Occlusion is now available outdoors, even in direct sunlight. You can see here how Live View in Google Maps uses long-range depth. The destination pin is properly occluded when it is behind the world and gets revealed, just like a real object, once it should come into view. This experience is currently rolling out in Google Maps, and I look forward to seeing what new experiences you build when using the depth outdoors. If you want to learn more about how we leveraged ML for improvements to AR Core, see our talk, What's Under the Hood in AR Core. And now, I'll hand it over to Eric to talk about the new exciting cloud services that we are launching.
Thanks, Jared. We believe that geospatial, three-dimensional, and world-encoded information will transform the way people learn, navigate, play, and experience the world together. Data shown this way feels more helpful, more understandable, more human. And to that end, we have been consistently focused on building cross-platform cloud services that allow developers to add augmentations anywhere in the real world, making the real world into a virtual canvas. In 2018, we launched Cloud Anchors, enabling multiple users to simultaneously share a single AR experience. In 2020, we followed up with persistent Cloud Anchors, which persist for up to 1 year. Cloud Anchors allow you to build a rich, persistent set of AR content in the real world that many different users can see and share. Cloud Anchors are best used for room-scale AR experiences, where you can be present at the place, in person, to host a Cloud Anchor. Many of you ask for world-scale capabilities, and today we are releasing the first set of ARCore geospatial APIs, enabling world-scale, shared AR experiences that can be authored remotely from your desk for both Android and iOS. With the ARCore geospatial API, AR apps can now calculate the latitude, longitude, altitude, and heading of your phone with greater accuracy than the GPS sensor can provide. This allows you to place geospatial anchors for virtual objects. Geospatial anchors are tied to a specific GPS coordinate, so they can be placed anywhere in the world without you having to go there. This is powered by Google's global localization technique, combining Visual Positioning Service, or VPS, Street View, and machine learning, so it works all around the world. This uses the same technology powering working navigation of Live View in Google Maps. Let me explain you how to use the API. I want to create an experience with a virtual object in a park near my home, right next to the sundial here. I'll need to figure out the exact latitude, longitude, and altitude for the anchor. This can be done from the comfort of your own desk using Google Maps. The specific steps are described in our developer page. Here are the geospatial coordinates of the sundial. These coordinates can get persisted into my apps database. When configuring the ARCore session, make sure to enable the geospatial API. This only needs to be done once before AR is started. And when a user enters AR, I use the sundial's coordinates to create a geospatial anchor using the new Earth Create Anchor API. And I'm done. The geospatial API enables location-based virtual objects for anyone, anywhere, on Android and iOS. This can all be done without having to map out each location, enabling constantly evolving dynamic virtual objects to be added to the real world. This is our next step towards building a helpful and useful AR for everyone. If you want to learn more about the Geospatial API, check out our talk, VPS and ARCore Geospatial API. Good AR seamlessly integrates virtual objects into the real world such that they are indistinguishable from real objects. To enable this, we've been leveling up the ARCore skill tree, both adding new skills as well as making our existing capabilities faster, more accurate, and available to everyone. By combining these capabilities, you can build compelling new AR experiences. I hope you're as excited as I am about the future of AR. If you want to learn more, please check out our developer resources and samples, as well as our other talks. Thank you so much for your time, and I can't wait to see what you build next.